Welcome to this video presentation on heat exchangers. Today we'll be analyzing example 4, which involves an oil cooler and determining the appropriate heat exchanger type and its surface area. Let's look at the problem statement. An oil cooler in a lubrication system needs to cool 1000 kilograms per hour of oil, which has a specific heat capacity of 2.09 kilojoules per kilogram degrees Celsius from 80 degrees Celsius to 40 degrees Celsius. Now, this is achieved by using a cooling water flow of 1000 kilograms per hour entering at 30 degrees Celsius. We need to choose between a parallel flow or counterflow heat exchanger, providing reasons for our choice. Additionally, we must calculate the surface area of the heat exchanger, given that the overall heat transfer coefficient is 24 watts per square meter degrees Celsius. Now, for water, assume a specific heat capacity of 4.18 kilojoules per kilogram degrees Celsius. Now let's begin with the solution by outlining the given parameters. Now the mass flow rate of the hot oil, mH dot, is 1000 kilograms per hour, which is approximately 0.2778 kilograms per second. Its specific heat capacity is 2.09 kilojoules per kilogram degrees Celsius. Now the inlet temperature of the hot oil is, that is TH1 is 80 degrees Celsius. And its outlet temperature TH2 is 40 degrees Celsius. For the cold water, the mass flow rate MC dot is 1000 kilograms per hour, which is approximately 0.2778 kilograms per second. And its specific heat capacity is 4.18 kilojoules per kilogram degrees Celsius. And the inlet temperature of water, TC1, is 30 degrees Celsius. And the overall heat transfer coefficient, U, is 24 watts per square meter degrees Celsius. So our first step is to find the outlet temperature of the cold water, TC2. Now we apply the energy balance principle that the heat lost by the hot fluid equals the heat gained by the cold fluid. So MC H dot times CPH times TH1 minus TH2 equals MC dot times CPC times TC2 minus TC1. So substituting the values and solving this equation, we find that TC2 is equals to 50 degrees Celsius. Now let's consider the choice of heat exchanger type. We have calculated that the cold fluid outlet temperature, TC2, is 50 degrees Celsius. This temperature is higher than the hot fluid's outlet temperature, TH2, which is 40 degrees Celsius. This condition, where the cold fluid exits at a temperature higher than the hot fluid's outlet temperature, is only possible in a counterflow arrangement. Therefore, a counterflow heat exchanger must be used. This diagram visually represents the temperature profiles for a counterflow heat exchanger. Notice how the hot fluid enters at TH1 and cools down to TH2, while the cold fluid enters at TC1 and heats up to TC2. In a counterflow setup, the fluids flow in opposite directions, allowing for a larger overall temperature difference and more efficient heat transfer, which enables the cold fluid to exit at a higher temperature than the hot fluid's exit temperature. Next, we calculate the logarithmic mean temperature difference, LMTD, denoted as theta m. So for a counterflow heat exchanger, The logarithmic mean temperature difference is given by the formula in the screen. And when we substitute the values, we get that the LMTD is approximately 18.2 degrees Celsius. Finally, we can determine the surface area of the heat exchanger, A. Now we use the total heat transfer rate formula, which is Q equals to U times A times theta M. So once we substitute and plug in the values, the only unknown is A. And when we solve for the heat transfer area A, we find it to be approximately equal to 53.16 square meters, and that is the final answer. And thanks for watching. If you found this video helpful, please consider subscribing to our channel for more content like this. Don't forget to hit the notification bell so that you don't miss out on our latest uploads.